My name is Amy Kucera. I'm a math major, as I have stated in previous speeches, and I will be demonstrating a mathematical proof. But before we can get into the actual proof, we need to determine what a proof is. A proof is a demonstration of truth. There are a variety of methods to assist in proving a statement, such as theories, lemmas, definitions, and axioms, which I will get into later. A proof is able to concrete abstract thought by turning examples into general statements that are validated in specific cases, which we define at the beginning of the proof with a let or assume statement. These statements are meant to display a general acceptance of the idea from which the writer builds their argument. Additionally, the use of phrases such as let and assume give the ranges of where the proof holds true. The next question to address is, why do we prove? Proofs not only benefit mathematicians, they also improve critical thinking. Proof forces the reader and the writer to question everything that they assume to be true and grounded in logic. Additionally, proofs force the reader and writer to explain their thinking process in a more in-depth and logical manner than they previously would have. Proofs take universally accepted axioms and form logical arguments, which hold in predetermined cases which are established in the beginning. These axioms include properties such as the commutative property, where a plus b equals b plus a, which is accepted universally true for integers, in which we will be working with today. Now that we have discussed what a proof is and why we should prove, let's get into an example. The first line, let x and y be non-zero. This statement gives the ranges of x and y being within the set of numbers including the integers. We then start off the argument by stating x equals y. We are then able to perform algebraic manipulations as long as it is done to both sides of the equation and is accepted to hold in the given parameters of the integers. This is where the axioms come in. We can use properties such as addition, subtraction, etc., because the axioms state that they are logically correct within the bounds of the integers. Other proofs may use lemmas, other theorems, and axioms, as we are using. The former two must be proven true before being used, as to raise the question to the reader, why does this make sense? With this in mind, we can then multiply both sides of this equation by x, giving the equation x squared equals xy. Similarly, we can subtract y squared from both sides of the equation, giving x squared minus y squared equals xy minus y squared. Note here that we are using the axioms of integer multiplication and subtraction to manipulate our equation. Then, dividing this equation, both sides, by x minus y gives the equation x plus y equals y. And at the beginning of the proof, we have the statement x equals y, which we can then substitute into this equation, giving 2y equals y, which then proves that 2 equals 1. Then subtracting 1 from both sides gives the equation 1 equals 0. The QED shows that you have reached the end of the proof. QED is short for quod erat demonstrandum, which loosely translates to that which has been demonstrated, marking in our proof that we have reached what we wish to prove, 1 equals 0. As you can see, there is nothing mathematically wrong with this proof. However, we all know that 1 does not equal 0. Although this proof does not logically make sense, it shows you how one should think critically and think logically about everything you are told. As I have just shown you, you believed everything that I was writing on the board to be correct. However, when you see 1 equals 0, you should be trained to ask why this happens and why this doesn't make sense. So I challenge you not only in your math classes, but also in your core courses to ask your professors their reasoning behind why they believe these general statements to be true, and to use more critical thinking in your daily life. Otherwise, you'll just believe that 1 equals 0 simply because a nerd told you so.